Okay. Um, I'm assuming this is rolling, so we get straight into it. So hi guys, this is the review session for IE 135. MAM J resurrections coverage of midterms. So that is from pretty much LE topic one um up until attributes control charts. Because the first few lessons are pretty much objective type. Um, Not much thing we can review there. It's really just brute force memorization. So we'll focus on two subtopics specifically, uh, variable control charts and attributes control charts. So yeah, I guess we can just go straight into it. Okay, so control charts for R are to be set up in important quality characteristic. The sample size is n equals 5, and X bar and R are computed for each of 35 preliminary samples. The summary data are una is the sum of all um, the quality characteristic, and the range, total range is 1,200. So first, uh, we need to find the control limits for X bar and R charts. Uh, okay, so going here. So n equals 5, 35 samples, and this is the given, um, wait, sorry, let me connect my phone. This is the given sum and sum of R. So una, we want to find the control limits. So, okay. So, recall lang how to set up a uh, uh, how to set up a control chart. Essentially, ito lang naman. So if the specification is a bit available, uh, we can either do mu plus a uh, a sigma or x double bar. This is the you can think of this as the average of averages, and then times plus minus a to r. Yung mga letters, these are constants that you can find on a lookup table. Um, so that's for yung X bar chart. So if the spec is available, use this. If the spec is not available, use this. By spec, I mean like yung parameters, mu, which is your population mean, and sigma, which is your population standard depth. Um, yeah. So for the R chart naman, the UCL is given by this. So just multiplying big D sub 2, small d sub 2, and big D sub 1 by population standard dev. And then same thing for the range. Ito lang yun. In this case, again, these are just lookup tables. Really, the only thing we can do here is to memorize when to use them. So for X, uh, for X bar R charts, this is what you need for X bar, essentially. This is what you need for X bar, essentially. And then this is what you need for R bar, essentially. So because there's no provided population mean or standard dev, hence the initial sampling, we use the second option, which is this. So moving on to that, now we know that what we need to find is X double bar and R bar. So because that will set our control limits. So looking for that, again, X double bar is just the average of averages. Given na our sum of X bars is this, and our samples is 35, we just have to divide 2. So that's why it's 7805 over 35 gives us this 2 to 3. R bar naman is 1200 over 35. These are just the sum of the ranges over the average. So we get the R bar, which is the average of the ranges, which is this. So then we need to get the UC upper control limit and lower control limit. Then we just use this chart for averages, deviations and ranges. So again, it's just a matter of knowing which one to use. So in our case, when we're building the control limits, So again, to build this control limit, recalling this equation lang that we figured out kanina. Uh, so I'll just put this. Oops. Wait. Okay. So x double bar plus minus a sub big A sub 2 times r bar. So this is x double bar. This is a sub 2. And then this is r bar. So nothing naman na we did here. Super particularly plugging in values now. So I guess the only thing to discuss is how we got 0.577. Uh, so we just have to use the lookup table to find for n. N, by the way, kasi there's a distinction already. We got 35 samples, but n doesn't refer to the number of samples. Well, in the large scale, it doesn't refer to the number of samples. It refers to the number of replicates per sample na kinuha nyo. So in this case, don't use n equals 35, use n equals 5 because, yeah, uh, yung 35 samples, they had 5 samples. Parang 35 repetitions, 35 samples, 5 replicates inside. So, ayan. Just be wary of that. So then we got a sub 2, which is just 0.577. Plugging that in, we get this as the UCL and this as the LCL. So that's pretty much the X bar chart. You just have to, yung next lang na gagawin is to essentially plot these, set these as the control lines. So when you build the chart, oops, sorry. So when you build your control chart, just set your UCL like as a red, like as a red line, LCL, and then your center line, oops, sorry, center line, and then everything else should logically follow naman. Same thing with your R bar. Oh yeah. So that's for the X bar pala muna. For R bar naman, we follow the same process. So R bar is D sub 4 R bar for the UCL, for the LCL, D sub 3 R bar. So again, using n equals 5, we just pull these values up, and that gives us these values. This just becomes a 0. Okay, so pretty much that's it. And then same thing with the drawing nyo siya, and you plot the points accordingly. So it's just a matter of plotting the data that you find. So that's for sub problem A. For sub problem B, assuming the process is in control, estimate the process mean and standard deviation. So the mean is just x double bar, which is 2 to 3. The standard dev is not given, but again, there's a way to estimate the standard dev. There are two ways actually for X bar charts. The first is either R over small d sub 2 or S over C sub 4. In this case, because we were working with ranges, it makes more sense to use this equation. And then just putting that equation. So this is just R. I just use the unsimplified version. We do not have decimals over d sub 2, which we can find over here. Uh, sorry, yeah, factors for central line. Okay, so then that yields us this equation. Uh, okay, just to write down. So then down pala. 14.7402. So yeah, relatively straightforward pa naman. Right. Here. C. Let's put this up item C. 15 successive, sorry. If the quality characteristic is normally distributed and the specifications are as follows, can the process meet the specifications? Estimate the fraction non-conforming. So essentially what we are asked to find here now is, so my process tayo na yung mean is, so the process, so we check if process as it is fits spec. So meaning yung process mo will dictate what the mean is and the standard dev or the standard dev, and then the spec defines your boundaries. In this case, I don't know let's see this one. Ayan, the boundaries. So then, in this case, this is just a matter of essentially finding the percent non-conform, which is just this. So you have a mean of 223, you have a standard dev of 14.7402, and you're looking for the percent that it falls outside the bounds given. So therefore, it's just 1 minus p times this. Technically, you can plug this in sa calculator na if you know how to. But just to show the how to break this down further, you can then get 1 minus uh ito is broken down here, and then ito is broken down here. Why is it this minus this? The reason for that is essentially we can get this by getting this. We can essentially get this. Wait. We can essentially get this by taking this minus this. Yun lang yun. So, yeah. As such, the answer is 0.1994. Okay. So that's, yeah, question number 4. If the process mean shifted to the center of the specification limits, what would be the average run length of the process given that you're still using control limits in A? So, going back, performance metrics. So the average run length is just 1 over alpha. So these are the common average run length, average time to first signal, and number of units to signal, not first signal. So essentially, alpha here just represents the area outside. Use the upper control limit and lower control limit. Okay. So then, just setting up the problem. Essentially, what this is what it looks like. You have now shifting process means we have 220, and then you have 203 here, and then you have 242 here. So then this is it. This is how you set it up. But just to be clear, the problem context here is that so the process is in control, and then nag-process shift ka, so it became out of control. And then you want to get the ARL, or how long it'll be not detected, while it is out of control. So there's the important distinction between type 1 and type 2. Don't mind the pictures, or I guess mind the pictures. That is essentially what they are both each. And what we are basically choosing between is, do we want to check the probability that the system says it is out of control while it's actually in control? Or do we want to get the probability that it flags the process as in control, even though it is out of control the entire time? In this case, nag-process shift ka, and then you want to check if it is out of control. In this case, we will do uh, beta. So that's the probability of seeing that it's in control, considering that it's out of control. But remember, yung tinatanong is, uh, how long it would take before we get the first signal, meaning the first signal, it's out of control, given it is actually out of control. So we want to get the amount of time it takes, the probability. Now it will be flagged as out of control, given that it's been out of control, which is 1 over beta. And that's what we plug in here. So solving then for beta, uh, we just use the equation given, which is this. So this is an equation given in class. And then essentially L and negative L are just 3 and negative 3 respectively, because that's the usual convention among 3 sigma limits. And then you adjust the mean shift uh, to a factor of k. K is just given by like how many nag-shift you mean in terms of standard dev times square root of n. So in this case, it's 223 minus 220 over s, which is the standard dev. you should get this answer. And then essentially when you solve for that, this is what you get for beta, 0.9943. Because when you plug it in you also plug it in sa calc. So you can get a value for this and you can get a value for this. So this is for those who are shortcutting using sa pictures of calc, this is basically your upper and this is your lower. And then you set u equals 0, sigma equals 1 in the calc. So then, yeah, that's it. Okay. So then, um, that's that. And then the average run length, therefore, is just 174.2029 units, rounding it up to 175. So that's the answer for number 1B. For number 2 naman, wait, let me look for it. Yeah. So we're given this setup. Let me just read the question. A process to be monitored, the standard values mu equals 10 and sigma equals 2.5. The sample size is 3. So then it's just center line and control limits for the X bar chart, the R chart, and the S chart. So it's relatively straightforward, just plugging in the values. So let's go to the X bar chart. The control line here is just 10 because that's the mu. So that's the mean. The lower and upper control limits are just given by mu, mu plus 3. And this is essentially your sigma or standard error, which is just 2.5 over square root of 3. So then you get these values. So it's relatively straightforward for the X bar chart. For the R bar chart, same thing, D sub 2 and D sub 1 are the ones we are most interested in. So uh, yeah, so the D sub 2, D sub 1, we look for that here, D sub 2, and D sub 1. So then just multiply that with R bar, which was given. Oh, sorry, with sigma, which is given. Sigma. This gives us those control limits for R bar. For S naman, um, yeah. So same thing, sample size 3. The only difference here is that this 2.276 is D6. So D6 times sigma. 0.8862 is C4 sigma. And LCL is 0 times 2.5, which is B5 sigma. That's it. So yeah, number 2 pretty straightforward naman. Uh, so yeah, that's essentially what you do. For number 3 naman, yeah, just checking. Number 3, 15 successive heats of a steel alloy are tested for hardness. The resulting data are shown here. Set up an IMR with MR equals 2 chart for the hardness measurements. So yeah, essentially, so going back to our X bar chart or our center line, this is just given by our X bar equals our X bar plus minus 3 standard error. This is just 3 sigma. This is yeah uh sample standard population standard depth over square root of samples. Problem is we don't have that, but remember, uh this entire term can be approximated by the moving range average over d sub 2. So okay. So this is just manual calculation work. Essentially what you just need to do here is get the average here. Yung moving range is essentially it is the absolute value between one and the next. So you'd have an MR chart here starting from point 2. So then you'd have 1, you'll have 3, right? 54 minus 50, 52 minus 51, absolute value 1, 51 minus 54, absolute value 3, 54 minus 55, absolute value 1, 55 minus 50, absolute value 5, etc. My formulas naman sa spreadsheet function sa calc. So there's a way to do this quickly. I guess I'll just fill this. So, okay, then you get the average of that, and that should give you this 3.2142. And then your D sub 2 is 1.128, um, as per what you found here. So then you have everything to build it now. The LCL is just that, 44.7180. Nakuha ito by getting X, by using this equation on the plus side, the minus side, and then this nakuha mo by using the plus. So yeah, that's essentially for the I, individual averages, individual samples, and then for moving, and then for the moving range control limits, this is just D4 times MR bar. So this is D4, this is MR bar, and then D3 times MR. So it's 0 times. So this is what you'll get. And then you can graph these accordingly. Yeah. Okay. Number 4. A normally distributed quality characteristic is monitored through the use of an X bar and S chart. The charts have the following parameters, and at n equals 6, both charts exhibit control. So that's the values, and then we are expected to find the mean and standard depth of this process, and then yeah, okay, yun muna, mean and standard depth of the process. So again, at this point, these are all just substitutions that we need to be aware of. So the mean is just the sample mean that we found. So this is 706. This was found in oh, cell center line. This is that. And then uh yeah. Oh, so yeah. And then S is just so standard dev, we don't have the exact standard dev, but this can be estimated using the property that we know, which is that S is equal to C for sigma. So meaning we can rearrange that to get sigma equals S over C4. This is our S from the given, yes, 738. And then C4 for six samples, for six sample size per sample. Basta like six replicates in a sample. 0.9515. So then this is the value that you get. Yeah. So that's for the that's for the S. That's for the for sub A. For sub item B, suppose an R chart were substituted for the S chart, what would be the appropriate parameters of the R chart? So the R chart, again, since we have an estimate for sigma, we can use that, right? So that's why sigma yung gamit dito and hindi S. Uh, Essentially, well, I think you would get similar results if you use S anyway, but I think that's where the problem is heading. Uh, so lower control limit is just D sub 1 times sigma. So D sub 1 in this case is this. D sub 2 sigma is D sub 2 times sigma, which is 1.8266. Then you get this value. And center line is small d sub 2 times sigma, which is this. And therefore you get that. Therefore you get 4.6289. Again, you can just plot these charts, and that will be the chart. So yeah, that's for number 2. For number 3, estimate the natural tolerance limits for the product. The natural tolerance limits is just plus minus 3 sigma, which is mu plus minus 3 sigma, which is approximated by x bar plus minus 3s. So that's just this. So this is just what we found kanina, my minus 3s, my plus 3s. Yeah, so that's basically it. The reason why we didn't use sigma here is because we don't have mu. Mu is not, 706 is not mu because we know that it's only coming from a sample that yes, we know is in control, but it's, ultimately not, uh, it's ultimately not a valid estimator it is an estimator, but it's like, mismatch siya. So just use X bar and S. If the specification limits of the product were 703 and 709, what would be your estimate of the of the process fraction on conforming? Oh my God. Okay. Uh, oh well, that sucks. Okay. I'll just continue. I think I'll send the file para masabayan niyo. Oh my God. Okay. So whatever then. Uh, okay. What is the 703 and 709? What would be your estimate of the process fraction non-conforming? So essentially, the limits of the product are 703 and 709. What would be your estimate of the process fraction non-conforming? Meaning, essentially, you would have this type of setup, and then you just basically get the probability that it will exist outside both those. 706 remains as is, because where did I show that? And so essentially, kasi what you're checking if the process fits the specification boundaries. So the process will dictate the mean, the boundaries will dictate the limits on the left and right. And so essentially what you're looking for is this. This can be also expressed as 1 minus 703 less than x less than 709. Yeah. So then gives you this probability. Uh, yeah. Detecting shift. So, okay, kailan ko pala. And last, what is the probability of detecting a shift in the process mean to 702 on the first sample following the shift given that sigma remains constant? So, uh, essentially what you're checking here is yung power of the test. How can you detect the shift instantly? Uh, so again, beta represents the probability that the probability of you thinking it is in control when it is not. By TPR, the probability that something is detected in control. Uh, so by TPR, P A given B is equal to I plus P A naught given B is equal to 1. Therefore, if you include P not in control, so meaning na detection na not in control, given that it is not in control, these add up to 1. Kaya siya 1 minus beta. Uh, I have an equation for that, plugging it in. The only challenge here is to find K. K is just the new mean minus the old mean over sigma, because we just want to find out gaano kalaki yung deviation in the mean given in terms of sigma, in terms of the relative to the population standard there. Again, this is plug in a ball sa calc as sigma as essentially your upper is the left and then your lower is the right, and then set mu equals 0, sigma equals 1. Because essentially what you're doing here lang is normalizing it. You'll get this value. So yeah, that's for the first four items. Sorry for again not being able to screen share the first parts. Hopefully masabayan niyo pa rin siya in some way. Yeah, sorry, I don't have time to re-record. I'm like super busy. Okay. 5. Plastic bottles for liquid laundry detergent are formed by blow molding. 20 samples of N equals 10 bottles are inspected in time. Order of production and the fraction detected in each sample is reported. The data are as follows. So this is samples. So we have 20 samples of N equals 100. So set up a P chart for this process is the process and statistical control. So first, we basically have to set up the P chart. In this case, let's just look for the values associated. Una, we get first P, not P bar. This is P bar. How did we get that? Una, um, this is not in unlike X double bar, which is the average of averages. This is you basically add them together. So you take the sum of this whole row and you divide it by n equals 100 times the number of samples. In this case, you will get the same answer even if you average yung kada P, but it matters when the sample size is different now. When the sample size is different, you want to add first the number of the defective or non-conform, and then you divide by 100 or well, then you divide by the total samples in the whole thing. So you don't uh, divide individual piece per sample. So when the sample sizes are different. So yeah, to get the upper and lower control limit, we get our P bar plus 3 sigma. So this is just the equation for the standard error for the sigma like standard error for the process not T, which is just T minus 1 minus P over 100 over N all squared. Ay, yeah. Kasi without the square root, it's the variance. So ayan. Plugging that in, you get this for your LCL, this for your control limit, which is just again P bar, and then UCL, which is 0.2039. So yeah, that's the that's essentially the limits of your P chart. Is the process in statistical control? We check essentially if lahat ng numbers pasok sa 0.0161 and 0.2039. So meaning, this translates to, do we have samples that are lower than 1.6 defective and more than 20.4 defective? I rounded them kasi whole numbers na naman lang. So checking if we have any excess here. Our lowest value is like 5. So wala tayong lumagpas sa LCL. Our largest value is 18. So wala tayong lumagpas sa UCL. Therefore, the process is in statistical control. For the smallest sample size, it will give a positive lower control limit. Essentially, this is just the formula for it. The derivation for it, I believe, is just you get the probability. So for the UCL is given by P minus 3 uh, P1 minus P n. You want this to be greater than or equal to 0. So moving stuff around, you get P, uh, you get P squared. This is just L plus, sorry. L. Then this becomes 1 minus. Um, then you move it around. So ita transpose ko siya to the right hand side. P squared, L squared, P, 1 minus P. Then I multiply both sides by n. So magiging n. So magiging ganito. I divide both sides by P squared. So then makakancel yung isang P. So, oh my God. Yan. Yeah, that's basically it. N has to be greater than that, not E. In theory, pwede equal, pero generally kasi you get a decimal, right? So anyway, this is just the probability that you have conforming or non-defective, probability that you have defective multiplied by L squared. So then you get this always round up. Yeah, just for B. Of course, 5 sub C. What is the probability that a shift in the process will average up to NP equals 15 will be detected on the first sample following the shift? This is where it's tricky because you can't just use the direct substitution na, yung shortcutted na 1 minus 1 minus Gaussian of 1 minus Gaussian of L minus K sub K squared of N minus Gaussian. You cannot use this one. This is the parang stock default, right? And the reason for that is um this assumes constant standard deviation. Uh, with P charts is that when the probability of defect changes, the standard deviation also changes. The standard error also changes. The reason for that is your standard error, recall, is given by square root of P times 1 minus P over N, meaning magbabago siya. So meaning you have to use the original equation, which is uh, Gaussian, 1 minus Gaussian, UCL minus UCL minus new process shift, new minus new P over uh, T new, this is the new P, 1 minus P over N. And then replicate the same here. Yeah. So then, in that case, this is essentially it. Uh, Kamali ako ng kopya, sorry guys. This is 0.0161. Ayan. So that's basically 5. Uh, yeah, okay. That's 5. Just checking. NP equals 15. That's the reason why 0.15 siya here. Because N is equal to 100, right? So NP equals 15, meaning P is equal to 15 over N, which is equal to 15 over 100. Okay. So that's basically the only thing there. And then ito yung lalabas. So that's the probability that that's the probability that you are able to detect a shift in the process. Because we're just looking for again T na detect mo na there's a shift or out of control given that it is out of control, which is just, and again, beta is just P equals in control given that it's actually out of control. So 1 minus beta. That's what that's for 5. For 6, a control chart of nonconformities is to be constructed with C equals 2.0, LCL equals 0, and UCL such that the probability of a point plotting outside control limits when C equals 2 is 0.005. So essentially, we want to find the probability that x is greater than a such x, the probability of finding an a such that the probability of x greater than a is equal to 0.05. Why is this the case? Because we want to find a UCL that essentially when c is equal to 2.0, we want to find so LCL is 0, UCL this is 0.005. Okay, but you might think, hindi ba kahit 0 siya, may some small thing pa rin dito. Pero recall, this is a control chart for nonconformities using C, meaning this is a C chart. And the C chart is based on the Poisson distribution with the mean equal to C, meaning, and again, I think this is also in 143. Pag Poisson, the probability of x at 0 is equal to 0. So nagsistart siya at 0, yung Poisson distribution, something like this. So we're allowed to basically look at it from one side lang. We want this to be 0.005. Okay. So then you can also change this to Poisson x less than a equals 0.95. Uh, okay. I have to show. Poisson CD. Wait, let me just get my calc. Okay, but essentially, may feature kayo sa calc called Poisson CD. How do I make myself visible? Okay. Oh, what the hell? It's a very small window. Yeah, I mean, I envy also. Shit. Okay, ayan. Sorry, it's a very small window. Uh, so you go to here, and then you go to distribution, click 7. You go to Poisson CD. You go to list, and then essentially you have, oh, wait, 7 CD kasi cumulative. Yes. So you have a certain, like you just want to basically test all the possible values. So test 0, 1, 2, 3, 4, let's say until 6. And then given our C equals 2, so our lambda is 2, it will basically output the probability. So given we make a request for certain X values, it'll give us the cumulative probability of each. So in this case, we wanted 0.005, meaning we were looking for the number. So we wanted 0.005 on the tail. So essentially, yung hinahanap natin dito is this entire cumulative area is 0.995. The first value that gives us that is x equals 6. Kaya yun yung value niya. Yeah. Sorry, medyo sloppy yun na din. But I hope that was helpful. Okay, so that's for number 6. For number 7, cover cases for a personal computer are manufactured by injection molding. Samples of 5 cases are taken from the process periodically, and the number of defects is noted. 25 samples follow. So, yeah, samples of 5 cases. So n equals 5 and number of defects. Okay. Okay. So this one, this is obviously not about defects because you can see na no, their numbers like 8, 9. So these are not uh defects. I think that's one giveaway sign na it's not. So therefore, this is about non-conformities. So recall na lang, non-conformities and defects are or non-conformities and non-conforming are different because non-conformities just mean na there's something like off about the product, but that doesn't mean that it's like completely unusable. Same with defectives and defects. So, ayan, using all the data, find trial control limits for this U chart for the process. If necessary, revise your control limits. So, this is our process of making a U chart. The center line is just the U bar. So, bakit siya may- so yeah. Uh, okay. So una, we just have to find the average. So this is just the average. Uh, essentially you get the U bar from each and then you divide it. So there's a probability of a non-conformity, not a non-conforming, a non-conformity in the samples. And then the center line is just U bar. The lower control limit is just use equations for this one. Try to remember. Sorry, diniretso ko na to eh. Pero if you use the formulas, you will end up with these. And this is the more important part the question is asking. These are our lower control limits, so naging 0 to, and upper control limits, 1.502. The problem with this is, meaning, uh, given that we have 5 samples, so this is the, parang, yeah, this is the U bar pa lang. This is the U pa lang. You convert it back to number of defects. So this is uh, in terms of U bar. This is in terms of number of defects, meaning you have to basically multiply it by 5, which is you have to multiply it by 5, which is our n. So discard this amount. If you look at the list here, sample 14 and 23 violate this, and therefore we have to adjust. We have to remove it from the sample. So the new U bar, removing them is this. This is now the sum of without 14 and 23 divided by 23. I made this mistake a lot. Kung mag-remove kayo ng sample, syempre bababa yung n. So this is just 23 kasi nagtanggal ka ng dalawang sample. Replugging this into your equation, you will get a different LCL and UCL. Uh, so this is your lower control limit, this is your upper control limit. So again, we have to convert this by multiplying by 5 times. So we have to check again. Kung may lalagpas ng 6.5092, we have to discard it and essentially repeat the whole process. So luckily in our case, walang lumagpas ng 6.5, meaning this is now a set of samples that we can deem to be representative. So that's essentially the first part, control limits. You chart necessarily revise the control limits. Let's say instead na 5 cases lang. Instead of 5 cases, the sample size is 10. Repeat A and then explain how it changes your answers. So if n was equal to 10, una, given na hindi nag-change yung number of defectives, essentially ma-half yung U bar natin, yung average U bar, and then this is essentially it. Essentially, plugging in your LCL and UCL equations. So ito naman, this time we multiply by 10 because that's the n. So basically, we discard if it lumagpas siya ng 7.51. Same culprits as last time. Samples 14 and 23 violate this, so we have to change that split. Uh, so essentially, that's what changes. And then you can just recompute. You can recompute. So basically, the answer is, so una, repeat natin yung A. So you will have to recompute A again. So removing them ulit, you get 0.196. Plugging it into the LCL equation gives us this number, which we turn into 0 because it's negative 0.6509 per UCL. We discard all 6.5 and above. Wala tayong 6.5 dito, thankfully, so not a concern anymore. Yeah, so that's basically goods na to. So the answer to what changed is functionally nothing. We still had to remove 14 and 23. But syempre, nakita natin, nag-iba yung U-bar, nag-iba yung LCL, UCL, pati yung threshold for when we had to discard. So yeah, those are essentially the changes. Okay, this is relatively quick lang guys kasi this is like a subsection of the LE lang. So down to our last item. The textile mill wishes to establish a control procedure on flaws in towels it manufactures. Using an inspection unit of 50 units, past inspection data shows that 100 previous inspections had 850 flaws. What type of control chart is appropriate? Design the control chart such that it has a two-sided probability control limits of alpha equals 0.06 approximately. Give the center line and control limits. So, sorry. C chart is the most appropriate one. The reason for that is we are essentially checking. So, una, these are similarly sized. Similar yung inspection unit, and we're looking at non-conformities. So C chart makes the most sense here. So C chart is the answer to this part. Kasi C chart is obviously when you have probabilities of defects, not flaws. And then U chart is more used for uh, U chart is typically more like it has a separate use case. So yeah, just look into that uh, it's a little bit more. So yeah, that's basically Yeah, so that's for most appropriate chart. And then we design the control chart such that it has a two-sided probability control limits of alpha equals 0.06. So this is just us getting lambda. The alternate, mamaya na yung alternate. So then we try to look for alpha equals 0.06, meaning we're looking at the threshold of 0.003 on the left and then 0.997 on the right. This is 997 and 003. Sorry. So essentially, this is what it looks like kung i-graph natin siya. And once you do the same thing we did sa Poisson CD, testing like all the numbers, we'll get that the UCL is 14 and the LCL is 3. Uh, so that's essentially your defects. Alternatively, you can also assume a normal distribution because for certain values of Poisson, you can estimate it as a normal distribution. So in this case, it's the same process, 0.003, 0.997, sorry, 0.97 lang pala. Yan. Yeah, mali pala to. Yeah. And then basically, this is your upper, this is your lower. Um, yeah. You could also just do that. Alternatively, you can look for the z values that approximate that, and you will get that L. So essentially, you try to find the z value that yields 0.97. Same thing with 0.03. You will get 1.8806. And then, uh, yeah, and then using this value, you can get the UCL and the LCL uh, by plugging in the formula for C charts. So like C charts for LCL, UCL. You realize that you'll end up with 13.9834 and 3.016. Ulit. For the center line, it's just this. So yeah, that's for C chart. Okay. So yes, this is relatively quick lang versus the other review sessions because yeah, 135 is really just a bit of brute force, a bit of memorization. So yeah, regardless, I hope that was clear to all of you. Have a great week ahead, I guess.